Hey, all. Welcome. We'll give it a few moments to see if other folks join, but really appreciate y'all being here tonight. Um, yeah, I'll introduce myself a little bit more here shortly, but yeah, I'm John Griffith, coming to you live from a basement in central Vermont, and super excited for you all to be here tonight. Super excited to share with you the new work that we've been undertaking the data puzzles team to integrate new strategies, new data sense making strategies into our resources. And as you are well aware tonight, we're going to dive into one of those strategies, the Notice, Think, Wonder strategy. Um, I thought what I might do, because we're going to be this is a little different than the normal webinars that I run. I thought I would just add a link in the chat to the data puzzles instructional framework. For those of you who are maybe not familiar with that data puzzles instructional framework, maybe take a look at that in the few minutes before we begin. Um, but yeah, so we won't dive into the framework as much, and instead tonight we'll focus on some of the strategies that are a part of that framework. Great. Um, well, welcome everyone. I'm going to share my screen. If I could figure out how to do that and start the webinar tonight. Thank you all so much for being here, taking the time out of your day to join after a busy day of work in the classroom, where whatever it is you've been doing, it is really hard. I totally understand to come to a webinar in the evening. I myself have a 1-year-old and a 3-year-old up above my head on the first floor running around. So I get it, but I'm super excited to have you here this evening to dive into a new data sense making strategy, a kind of a spin-off of something that you're likely familiar with, the Notice, Think, Wonder strategy that we've recently added into the Not All Warming is Equal data puzzle lesson. So tonight we're going to collaboratively engage with that strategy in the context of this lesson. And like I was alluding to before maybe some of you joined, we're not going to dive into all of the parts of the lesson tonight, as that's a much longer webinar. Tonight we're going to look at the data visualizations that are part of that lesson and engage with that instructional strategy, the Notice, Think, Wonder strategy together. And so you can kind of envision what that would look like for your students in the context of these visualizations, and then hopefully you might leave inspired to try this strategy or maybe even this lesson in your classroom in the future, or with resources you develop in the future at a future PD. Hopefully you get something out of this. Yeah, that's the goal. For those of you that are new to data puzzles are hopefully concise, around 180-minute long lessons that combine classroom-friendly data sets with ambitious science teaching practices to support students make sense of phenomena. And in this case, we're going to be exploring visualizations kind of about the Earth's broader climate system, and we'll kind of let you uncover the secrets that come out of the data set for yourselves. I want to acknowledge that me, John Griffith, I'm a talking head for a hugely collaborative group. Um, I'm a former 8th grade science teacher and climate scientist, and my job now is I work for an organization at CU Boulder called CERES, the Cooperative Agreement for Research in Environmental Sciences, with the Education and Outreach Group. So CERES, my job at CERES is to work with scientists at CU Boulder and NOAA to bring their research into classrooms by developing resources like data puzzles. And tonight you'll get to meet one of those scientists, Dr. Jen Kay, who's an ocean and atmospheric scientist with CERES. She's the scientist that curated the data visualizations that we'll see tonight. And so she's going to be available in the last half of this webinar to talk a little bit about her work, to give the data visualizations. We'll explore some context and to be available to answer any questions that you might have. This work is also heavily informed by Dr. Melissa Bratton, who's also at CU Boulder. She's a co-author of the Ambitious Science Teaching textbook, and as you can imagine, hugely instrumental in the development of this instructional framework, which leans heavily on her work that she'd done previously. We work with about 800 Earth scientists at Ceres, and so very grateful for all of those folks and the time that they've given me and educators like yourself. And then so many other folks, the DataSpire team, Kristen Hunter-Thompson and Annette Brickley. If you don't know DataSpire, you should check them out. I'll add a link to the chat. They do such incredible work with teachers and science coordinators and administrators across the country, supporting teachers and bringing data into classrooms in really innovative ways. I'll add a link to their work now. Um, Dr. Jessica Bean does a lot of work with data puzzles in terms of making sure that the climate content is up to date, rigorous, but also age appropriate. And then teachers like you, we've worked with hundreds, if not thousands, of teachers over the 5 years that this work has been that we started this work. They've helped develop these resources, given us feedback. Pictured here in the bottom right, this is a group of 20 middle school science teachers from the Colorado Front Range who have taken a leap of faith to work with myself and the greater data puzzle team to integrate the strategies that you're going to engage with tonight into data puzzle resources. Basically, we're working with them to build their own data sense making skills. And as we're working with them, we're learning for ourselves what works and what doesn't work and modifying resources accordingly. So grateful for this team, and much of what you see tonight is heavily influenced by this group. The data puzzles instructional framework. All data puzzle lessons follow this framework. Should also mention data puzzles resources. They have slide decks, student worksheets, teacher guides, answer keys. Some of those resources are being modified right now as we add new strategies, add new data sense making practices, and make sure to highlight those features. But for the most part, they're meant to be plug and play. However, I want to note that they're not meant to be what I used to call in my 8th grade classroom, not to students, but to myself, to shut up in color. This is not a lesson that you just give out and say, go do it. These are meant to be engaged with collaboratively. You're going back and forth between the slide deck and the student worksheet. There are different small group and whole group discussions that need to be had. And that starts by eliciting students' ideas. All data puzzles start with an opening scenario. Um, it's usually a video or a prompt to get students thinking about an experience that they had that has science ideas similar to a new investigation they'll engage with later. So for example, if we're talking about the Arctic and changes in reflectivity or albedo of the Arctic, we might start by asking students to think about if they've ever gone outside on a day that was snowy and it was really sunny and snowy, like how did that make their eyes feel? Like describe that moment. What was that like? What did you go out? Did you go get sunglasses? Did you feel that way everywhere you were, or just where it was snowy? Getting some of those conversations out ahead of the lesson helps you understand where students are at in terms of their understanding of the science ideas they'll engage with later. You can connect with their experiences, their ideas, their language. And after eliciting student ideas about a scenario that they're familiar with, introduce a scenario perhaps they're less familiar with, which is the science investigation that featured scientists presented in a puzzle plot text. Basically, a 2-page background reading is actively investigating. And so students are going to hopefully make connections between their own experiences and this new scenario, this new science investigation. Um, they will develop initial models about an investigative question that's presented to them in the text and make predictions about that investigative question. And then this is where a lot of the big changes are coming. Students are testing their prediction against a classroom-friendly data set, but we're integrating new strategies to support students identify and interpret patterns and context, new sense-making practices. So how do we support students make sense of data? What does that mean? What strategies can we enact in our classroom to get students doing certain things with data in service of practices? And then how do we take all of that information that they have gleaned through these first three parts of the framework and put the pieces of the puzzle together to construct a final model? So again, all of this is in a student worksheet or a slide deck. There are answer keys and teacher guides, but all our lessons follow this kind of four-part framework influenced heavily by the ambitious science teaching framework. When we're talking about data sense making, which is a critical part of that third quadrant in the framework, we're talking about the data exploration, analysis, and interpretation completed to investigate a science phenomena. So all of these lessons are phenomena based. Students are actively trying to explain and model a phenomena, and it's the data exploration, analysis, and interpretation that's needed for them to be able to investigate and explain that phenomena. So what practices support this sense making of data? This is what Kristen Hunter Thompson and Annette Brickley of DataSpire have been doing for the much of the last year, actually. They've spent a lot of that year pulling apart the science and engineering practices and kind of pulling them apart so that there are describing those practices that are more specific to working with data and making sense of data. And so, for example, if we look at science and engineering practice, analyzing and interpreting data, SEP4, we wanted to think more deeply about how can we set students up for success with analyzing data. What does that even mean? We think that means describing patterns and interpreting, like we got to draw conclusions. And so what can we do to kind of call these two practices out more deeply? We're defining the aspects relative to SEP4, the data sense making practices, to be describing visual patterns and interpreting patterns and contexts. And so once we've broken down those SEPs into data sense making practices, we're thinking more deeply about the strategies that we can include in data puzzle lessons to build the skills around these practices. What strategies can we use to support students describe visual patterns? In all of our lessons, we're always starting with this describe visual patterns. We're trying to get students to build that skill at the forefront before any of the interpretation begins. And so to describe visual patterns, we can use learning strategies like notice, think, wonder. In a webinar last month, we focused on the slow reveal strategy. Next month, we'll focus on the zoom in strategy. So different strategies that can support this describe visual patterns, data sense making practice. Many of these strategies require students to do something with the data, or we want to challenge students. We want to challenge you to challenge students to have them do something with the data, enact something, do a move, do an action. In this case, with the data visualizations tonight, we're going to have you actually annotate and highlight features of the data, much like you would with your students. And again, all of that is in service of this data sense making practice. So whichever again, we've got quite a few data sense making practices, and we're just leaning into one tonight. But regardless, wherever you see a practice in a data puzzle lesson, there's a strategy that hopefully gets at that practice, and there's a data move or an action that students are engaging with to get at this practice. So we view all of these parts connected, and again, we're calling them out in all of our resources. Tonight, with the notice, think, wonder strategy, we think that this strategy aligns really perfectly with the SEP4 and allows you to go a little bit deeper with the analyze and interpret SEP there. For notice, we think you can break it down. Notice is just more or less what you see. It's the context. around a data set. You need some context around a data set in order to be able to analyze and interpret it. With regard to the analyze, that's the think. When you're analyzing a data set, you're thinking about patterns, and with the interpretation, we think that's the wonder. How do those patterns fit back into a context, or how am I making sense of those patterns through my own lived experience? So you're wondering these things, you're interpreting these patterns in the context. And all of these different parts, in all of these different parts, you're describing visual patterns. Something that's different, we think, than perhaps the way folks have traditionally done it, and maybe that's not true for you, but we are giving more specific prompts around the notice, around the think, around the wonder, and encouraging folks to really stay in those lanes when they're engaging students with this strategy. So, for example, if we're asking folks to simply notice or see things in the data visualization, trying not to we're trying not to hear any thinking about patterns. We want to stay in that notice lane. When we're thinking about patterns, we're just looking for patterns. We're not trying to wonder about how it fits into our lives or a bigger context. And one of the reasons for that is we want to give each student an opportunity to think and make their noticings, thinkings, and wonderings for themselves before being influenced one way or another. And hopefully we'll see how that plays out here tonight. What you're seeing here on the right, this is the interactive text, the puzzle, what we call the puzzle plot that provides some additional context to the data set. So all classrooms, all students are engaging with this text before making sense of a data set. In this particular lesson, students are describing visual patterns in a data set that's related to this investigative question. Are the places on Earth where atmospheric CO2 has increased, are those the same places where temperatures have increased the most? So the places on Earth where CO2's increased the most, are those also the same places where temperatures have increased the most? And for this first part, we can ignore this last name A through F. I'm going to just get the draw tool and cross that out. For this first part, what I'm going to ask you to do is to actually engage with this notice part of the strategy by highlighting and annotating features of this data visualization that you see on the screen here. And so again, we're focusing on the notice, which is what you see as it relates to these three different questions. In the bottom left corner of your screen, there should be, if you move down to that bottom left corner, there should be a little pencil with a green circle that will illuminate if you move your cursor over that pencil. And what I'm asking you all to do is to click on that pencil and find, it should be on the draw tool, but you can see this is kind of a fun way to get to highlight. I see Joanne in there. Thanks, Joanne. And I just want you to circle, write, draw lines, whatever you need to do to address these three questions, or whichever of these questions you're up for as it relates to the data visualization that you see. So I'm going to give you a few moments to do that. If you're someone that can't find that annotate tool, feel free to add your responses in the chat. But this becomes, I think, a lot more fun for you all, and again for your students when folks are in here annotating. I should mention too, for this lesson, we ask that folks actually print out the maps and have students annotate for themselves, much like you're doing here. So I'll give you a few moments to do that. Again, if you're not able to find that green circle, that pencil in the bottom left corner of your screen, you can feel free to type in the chat your responses here. So things that are jumping out, it looks like, to folks. We've got the legend circled over here. We've got numbers ranging from 107 to 123. Looks like the different colors represent different numbers. Uh, I see lots of horizontal lines. It looks like potentially those lines are um, separating out different color bands. I see one for like the southern hemisphere. I see another line in Antarctica here, one at the equator. See some blue circles around some of the darker colors here. See the type of data, the units are listed here and the range. Awesome. No worries. Great. So Eric's seen no date or year on this map. Thanks, Eric, for pointing that out. Awesome. So this is great. We're seeing lots of different things for ourselves. We want to make our noticings visual so that we can like visualize what other folks are visualizing as well. So in a classroom, again, you could see the student worksheet for yourself, but you might print this out. And again, the slide deck goes with these prompts, to ask students for themselves to look at the different parts of the map and think about the colors and to draw and annotate and highlight these different features. All right, so those are some of the noticings. You all did a great job not thinking. Thanks for not thinking. The thinking comes next. And again, you can just keep this annotate tool. Actually, no, I'm sorry. We're gonna do one more noticing. We're gonna do the same thing now, but this is for a temperature visualization. So again, you're back in with your annotate tool, doing the same thing. We're just see what do we see? What are the different parts of the map? How are the colors being used? What kinds of data are being used? Focusing only on the noticings and what we see. Cool. So I'm seeing kind of fewer lines, circles around regions that have different colors, some circles around regions that have like a darker kind of red color, others circled around areas that are that lighter yellow color. Units, I'm seeing the units being called out, different colors. This water is yellow. Okay, great. So lots of different things we're seeing, we're noticing, and probably many of you, given your experience and having analyzed many of these in the past, your minds are jumping in lots of different places. You're asking questions. I'm sure you're asking questions. You're thinking, you're trying to explain what you're seeing. And probably many of your students are doing that as well. And so we would encourage you, if you use this strategy or you facilitate this particular lesson, to try to just stick to these prompts and keep students in these lanes, as we think that this opens up the experience for all students. If students hear an answer, if we're already describing the pattern and explaining the pattern and the context, which some students might already be able to do, right, other students might kind of just shut down and not engage it as much. So would encourage you to slow down and again have students annotate and highlight in these ways. It really allows for everyone's noticings, everyone's visualizations to be public. All right, moving away from the annotate tool, now we're going to ask you to think. And for this part, I think what we'll have you do is just use the chat if you wouldn't mind. And perhaps you choose one of the questions on the screen to respond to in the chat. What are these data visualizations showing? How can you describe the variables? What patterns do we see in the data? Maybe we'll stick to that one. What patterns are you seeing? Different shades of red. You see one pattern Rhonda sees is that there's more red around the North Pole, more red in the Arctic. And I remember seeing some other folks circling during the noticing, circling different areas that had some reds as well. Again, looking at the two maps together, atmospheric CO2, Earth's temperature. Now we're looking at patterns in the northern hemisphere. Erica's talking about the purple is darker in the north, lighter in the south. Similar to the red in the north in the lower map. So a greater concentration, a greater change in atmospheric CO2 in the northern hemisphere, maybe greater temperature change in the northern hemisphere here, maybe, although we do see some significant temperature change in the southern hemisphere there. Darker pink compared to the southern. Right, so some of these patterns, medium, the lower map, well, greater changes near the poles. Okay, Joanna. So we're seeing, right, maybe the atmospheric CO2 change is greater in the northern hemisphere, but temperatures are changing at a greater rate near the poles in the north and south pole. Great. So you all are, this is fantastic. Thank you so much for your contributions here. CO2 is a band across the map, temperatures have pockets. Great. So we're seeing bands versus pockets, polar regions, north and south polar regions, maybe warming at a greater rate or warming at a greater rate than these other areas, these different pockets. And finally, so we've done our noticings. Now we've got some of our patterns, and now thinking about, we're starting to interpret, what could these patterns mean? Right? How could these relate to one another? And so given what you already know about the relationship between carbon dioxide and temperature, maybe you're starting to try to make sense of those patterns in that lens. Maybe you're someone who's thinking about how gases in the atmosphere circulate and how things are moving. Maybe you're thinking about residence times or how long certain gases stay in the atmosphere. Perhaps you're thinking about different feedback loops. So you know the Arctic has a lot of sea ice, and maybe a decline in sea ice has to do with warming here versus elsewhere. And so no matter where you are in your noticings, your thinking, like folks are going to have different ways to start to interpret those patterns, explain those patterns. And for you and your students in the context of this lesson, right? We're focused on this question. Are the places on Earth where atmospheric carbon dioxide has increased the most also the same places where temperatures have increased the most? And so if we go back to this graph, these data visualizations, we can see the greatest change in atmospheric CO2 is in the northern hemisphere and in these different pockets. But the greatest change in surface temperature is not in those same pockets. The greatest change in temperature is at the polar regions, little pocket here in South America. So what we're trying to do in this lesson is to get students thinking about the way Earth's climate system is all connected, and how what's happening in a few places, right? Largely the northern hemisphere, greater emission of CO2 by dense population centers, how the rise and change in atmospheric CO2 concentrations, maybe those same places aren't warming the greatest. And it's an opportunity to start to explore some different things, perhaps unequal heating of land and ice, or uh, how much CO2 different urban centers are emitting, different countries are emitting. How long is this change for? Great question, Carla. This is over a 100-year period. So this is the 2000 to 2014 average CO2 concentration minus the 1900 to 1914 concentration. So that's a change in atmospheric surface atmospheric carbon dioxide over that 100-year period, and the change in surface temperature over that same 100-year period. With this data puzzle lesson, before I turn it over to Jen, I just wanted to show what this lesson looks like for you. Here are those same data visualizations. The prompts for the Notice, Think, Wonder strategy related to these data visualizations are in the slide deck. And after engaging with that Notice, Think, Wonder strategy, both individually or in small groups, and then as a whole class, again, we want to share our thinking and make sure what we're seeing, what we're thinking, what we're wondering, that everyone gets to experience and share that. We're learning from each other. Then students go and are asked a few scaffolded questions, challenging them to really focus on the areas that experience the greatest change, greatest increase in atmospheric CO2 and temperature, and then ask them to revisit their prediction for the question, are the places on Earth experience the greatest change in CO2 also experiencing the greatest changes in temperature? The bottom, we have students construct a final model, an annotated sketch to explain their thinking related to the question, give them a few scaffolded prompts to think about how they might build a model. How might they show changes in temperature? We see a lot of students use thermometers or plus or minus signs. How might you show changes in carbon dioxide? Maybe you're using a CO2 molecule and it's bigger or smaller to represent change, big change or small change, or lots of CO2 molecules versus a few in different locations. So again, kind of make an opportunity to make those different patterns visual here, and then get to interpret those patterns in context with some digging deeper questions at the end. So again, this lesson is not meant to be plug and play. I mean, is not meant to be like just pass it off to students and say go for it. It is meant to be something that everyone is engaging with collaboratively. And that Notice, Think, Wonder strategy, we really hope with those scaffolded prompts and challenging teachers and students to stay in those lanes, the notice lane, think lane. The wonder lane gives everybody an opportunity to describe those visual patterns for themselves and learn from one another. Um, so that's that strategy. Uh, Again, the strategies in service of that describe visual patterns. And tonight, we're very fortunate to have Dr. Jen Kay here, who curated, who produced those data visualizations for us. And she's here tonight to talk a little bit more about her work, especially as it relates to the polar regions. Dr. K, thanks for being here. I'm pulling up your slide deck right now. Um, if you would like to take over the screen share and show the slide deck for yourself, you're welcome to do that, or I can move slides for you, whichever you prefer.
I think it's maybe easier if I do it. Hey, John. Hey, everyone. Thanks for taking the time and excited to be here and share some insights with you.
Yeah, thanks so much for being here, Jen. So again, Jen's gonna speak a little bit more about her work, and especially in the context of this lesson, and the data sets that she's curated, the maps that she's produced for this lesson, and then be available to answer some questions at the end.
Yeah, great. Hello, everyone. I'm Jen Kay. I'm a professor at the University of Colorado. And yeah, working with John on a National Science Foundation proposal. And part of that proposal included engaging and interacting and developing tools for you all. So I'm really excited to be here as a resource for you and to share a little bit about how my work has related to and inspired some of the tools that John has developed. So I'll give a short presentation, understanding Arctic warming using observations and models. And John, what are you thinking for time here? Something like 15, 20 minutes and
Yeah,
some
that'd be
questions?
great. Yeah,
Okay,
thanks, Jen.
cool. I just want to make sure I'm cognizant of time.
Yeah,
Um, and yeah, also just to kind of reflect a little bit on what I was hearing at the very end there. Science is a process of collecting information, collecting observations, using models. In this case, a lot of what I'll be talking about are numerical models. So I'm talking about solving equations on a computer that describe sort of the physical processes that are controlling these things. But I know also conceptual models come in. All of these really come together to improve our understanding of, the world around us. And the Arctic, as you've seen maybe from some of the maps that you've been looking at, is a region that's warmed a lot, especially in recent decades. It's about 4 times more than the global mean. So we'll look at some of the data that underlie that. And the Arctic is also a pretty remote place. Like, who's been to the Arctic? Like, it's far up there. And so the ways that we learn about it are important to think about, because it's not like, there's a major airport like the Denver International Airport there with, millions of people screwing around and, making observations. It's a pretty remote environment. So yeah, so I'll start. This is just the background here is a picture that I took actually on the coast of Alaska. So this
Jen,
is,
we can't. I'm sorry, Jen, we can't see
oh,
your screen.
is it?
Yes, we can.
Oh, you can? I
Yeah.
just can't. Okay, never mind.
Oh,
Great,
okay. Can you see it? Let's just double check. Cool. Looks like it's maybe okay.
Right.
Okay,
great.
great. So yeah, this picture is a picture that I took. It's actually looking off the coast in Alaska up towards the Arctic Ocean, and you can see there's some ice that started to form along the coast here. There's a polar bear wandering around. It's This is a remote and very interesting environment. It's a one that experiences a lot of seasonal change. So in the middle of summer, 24 hours of sunlight. In the middle of winter, 24 hours of darkness. The Arctic Ocean is covered with ice sometimes. That's called sea ice. Other times, it's unfrozen and it's open water. So a lot of interesting things there. So this is kind of like the boots on the ground. What do you see? But a lot of the data that I work with are actually from satellites. And so those satellites can, for example, just see exactly like what you see with your eye, but from space. So this is a view down of the Arctic Ocean. And we're looking at it's basically what you would see with your visible eye if you were above Earth looking down. And it's a mosaic, so it's a lot of different images that have been stitched together. So you'll probably see some places where, there's some differences, and that's just associated with the different stitching together of the different images. But you can basically see everywhere. And this image was taken June 21st, 2025. So just a couple months ago, right around sort of the peak amount of sunlight coming in the summer solstice. So we can see things like clouds. We can see Greenland, this big ice sheet. We can see the Arctic Ocean and the North Pole, which is, under the Arctic Ocean. So the Arctic Ocean is frozen. There's clouds on top of it. Those clouds and ice surfaces tend to be really bright. Whereas, if we can see down to the ocean or the land surface, it tends to be darker, maybe a darker blue if it's the ocean, or a darker green if it's the high latitude land. We can even see some kind of wispy stuff here that might be some of the Canadian wildfire smoke. We had a lot of that going this summer. And from space, we have this kind of data like every single day. So if you're ever interested in just kind of checking in with what you see when you look down at different parts of the planet, including the Arctic, that's really an amazing thing that we have to look at. So the next slide is showing the same thing, but actually for October 6th. So that was just earlier this week. And you can see some things are a little different here. First of all, on October 6th, it looks like over Alaska, there weren't enough images in that particular day, and so we don't have a full view of the entire Arctic Ocean and then the entire Arctic system. We also can see this area near the North Pole, which is dark, and I'll call this a pole hole, where we're not getting what's any observations there. And I wonder if people have an idea of what might be starting to happen. Why is it harder for us to see what's going on with our eyes with visible light at the North Pole in October than it is in, for example, in June? Any ideas?
Well, like you were saying that it's dark for 24 hours at certain times of year, so that might.
Exactly. So here we are getting into October, just like you all are all noticing shorter days, probably where you're living. If you're in the Northern Hemisphere, which I'm assuming you are, it's getting harder to see with visible light in the Arctic. And if you look at this same kind of image, for example, in January, you basically don't get any data, any information. So this is kind of a cool analogy for like the ways that we observe things and how there's ways that those are really powerful. And then also always a little bit incomplete, like we can't see in the dark. Like, so that's something we're not going to be able to do. So another kind of way that we can visualize what's going on is, of course, combining information from a lot of different places and making just plots that show how things have changed through time. So here, what I'm plotting are the observed Arctic and global surface warming. And this is basically shown as a departure from a long-term mean, and that mean is taken from 1951 to 1980. So what you can see is for the globe here in black, that especially, maybe since about the 80s or something like that, we've seen about a degree Celsius of global warming. But if we look at what's happened in the Arctic, this is basically over my lifetime, the Arctic has warmed more. It's warmed by, maybe almost 3 degrees. And so this is this idea that the Arctic is, experiencing more rapid change. But there's other things you can notice from this time series. First, what's going on in the 1930s? The Arctic was warmer then too, and it doesn't look like the globe was warmer then. And so, there's some variability that's playing a role here. We have to understand what might be driving these changes. Is it natural variability, or is it something that we're changing in the environment, like greenhouse gases? My short answer is it's always both. The variability is always there. And so when we add something like greenhouse gases or other small particles in the atmosphere that reflect incoming shortwave radiation called aerosols, those can also affect the system too. But it's really when we combine these observations over long time periods over the entire globe that we start to see really sort of convincing patterns that relate to sort of long-term changes in something like greenhouse gases. So the Arctic has warmed more. The globe has also warmed. The Arctic is a smaller region, so it has more variability. The globe looks more continuous through time, maybe because we're averaging over more regions and averaging out some of that variability. I also want to point out the observations that I'm plotting here are from a compilation that was put together by NASA called GISTEMP. But there are also 3, 4 other independent groups of scientists that put together the available observations, and they all come up with a pretty similar picture. Of course, there are not observations of the surface temperature everywhere, so there are efforts to kind of infill where there aren't observations using sort of the best practices and understanding of how regions vary together. And also these data are publicly available, and I also made the code because I had to write some computer code to make this graph from the observations. I made that code available on a service called GitHub, which is where a lot of scientists share their code So if any of you are interested in looking at that, the link is there below. Okay, so that's the observations. The Arctic warming more than the rest of the world. The actual question I'm often trying to address in my research is why? Why is that happening? And I kind of alluded to the importance of both, changes in long-term forcing, like the greenhouse gases, carbon dioxide, methane, and then also, small tiny particles in the atmosphere that reflect shortwave radiation. So for example, some of that smoke from the wildfires. But then also the variability. There's a lot going on to try to understand this. And I want to say that I really think understanding what's happening requires using both observations and models. And that is like what I have done in my work. So this is a picture of my boot on the ground, actually stepping in some Arctic sea ice. So I've gone up to the Arctic, I've made measurements. But I also use measurements from satellites, and I also, run numerical models, numerical simulations on large supercomputers, including those funded by the National Science Foundation, to try to understand not only what has happened, but also make projections about what will happen into the future. So some caveats here, observations are incomplete and all models are wrong. So it really requires putting all of this together to kind of develop an understanding of what's going on. So lots of ways to observe the Arctic, in situ, that's just this boots on the ground. We do have some long-term observatories in the Arctic, including on the North Slope of Alaska for the US. Other countries, some share their data, some don't. So, working on the ground, has its benefits, but it's also can be limited in the number of spatial points that you get. Satellites are amazing because, of course, they don't require you to go there in person. You can look from space. That gives you a perspective of the whole Arctic or the whole system that's very different. And satellites are, I think, a really powerful tool. But satellites only go back so far. The late 1970s is when many of the satellite records began. And so things like ice cores, where we can like drill into the Greenland ice sheet or the Antarctic ice sheet and look at the layers of snow that have accumulated over time to form ice. That can help us develop a record that goes back in time because there's some air bubbles that get trapped in that ice. And we can basically go back, tens of thousands of years and sample the air and see how much CO2 is in the air, or use some isotope geochemistry to figure out what the temperature was. So these all have their benefits, and I think, again, are really powerful when put together. In the background here, this is just an image of an employee at Ball Aerospace who's working on the Ceres instrument, the Clouds and Earth's Radiant Energy System. This is a system that measures radiation from a satellite in space. And one of the data sources that you guys have and can use as teachers, we've made some time series for you. And one of those time series includes how much sunlight gets absorbed in the Arctic over time. And that measurement comes from this Ceres instrument. Another way that we observe what's going on in the Arctic is by using other wavelengths of light. So in this particular example, we're detecting where the Arctic Ocean is frozen and where it is open water using what is called passive microwave satellite remote sensing. So this is a longer wavelength than the visible wavelengths that you can see. But also one of the benefits of this is you can see in the dark with this, and also you can see through things like clouds. And so that provides a lot of benefits in the Arctic, which is a very cloudy and dark place sometimes of the year. So this is the extent, so just measure of area of the Arctic Ocean that's covered in sea ice. So let's tell you where the Arctic Ocean is frozen. And it goes back to about the late 1970s, 1979 to be exact, and goes through present. And so you can see over time, there's been a decrease in the amount of Arctic sea ice. And, in the late 1970s, it was more like between 7 and 8 million square kilometers of ice. And now it's more like 4 to 5 million square kilometers of ice. You might ask, well, what's going on now? I actually just updated this time series working with a student earlier today. But looking at the September 2025, September 2025 actually is pretty similar to what we've seen in recent years. So we didn't have an extreme record minima, but the National Snow and Ice Data Center has the information. They publish the sea ice today. It's kind of like a update based on the data that they produce of where the Arctic sea ice is. And the daily minima in sea ice usually happens in September. This year it was in September 10th. And it was in the top 10 lowest minimas on record. So again, pretty similar to the conditions we've been seeing in recent years, which are a lot lower than when this record began in the 1970s. Just for some perspective on how much of a change that looks like, this is just mapping that on top of North America. So you can see what sort of the long-term average from 1979 to 2000 looks like. And then the lowest daily sea ice extent on record, which happened in September of 2012, there in white. I find these projections helpful for thinking about what this actually looks like over an area that I'm maybe more familiar with than the Arctic Ocean. Here, maybe I'll just briefly show you these, but there's a lot of ways to make your own maps at the National Snow and Ice Data Center. So, for example, you can look at the sea ice anomaly map, so the departure from the long-term mean spatially. And you can see, where the sea ice has been lost, where things are changing, and that can be really fun. A great resource, if you like to do armchair science, which I often like to. It doesn't involve any coding. You're just clicking and working with somebody else's kind of GUI-based version of the data. So I also work with other wavelengths in the Arctic, and I wanted to provide this because it's really neat. It's an active satellite mission that's called PREFIRE. These are two instruments that are the size of a loaf of bread. So they're CubeSats, and they're kind of less expensive, only $40 million, but also they're meant to be sort of more high risk, high reward for some of the work that we do with satellite missions. So these two CubeSats, they launched in 2024. They're just reaching the end of course, a couple of years of, almost getting into the second year of data, and it's really exciting. The goal of these satellites is to study Arctic heat loss to space, and there's a lot of great images and stuff in this YouTube link, including the actual launch itself, where you can kind of see the launch that was from New Zealand on an Electron rocket. And so you can see like the launch into space and then the kind of payload being deployed to measure Arctic heat. Okay, so I'll finish up here just by briefly talking about models. When I say model, I mean a numerical model. So I'm just solving equations, describing climate processes. Sometimes I can do that, on a piece of paper or on a whiteboard, but a lot of times it involves using a computer, sometimes a supercomputer, where there's millions of lines of code that are being solved. And those models are really helpful because they let you test hypotheses and do experiments and really try to make projections and understand what's going on. Yeah, so that's just what I said there. And I just want to say, you guys were talking about these data when I joined the Zoom, just like the spatial distribution of where it's warmed. and the spatial distribution of where surface atmospheric carbon dioxide concentrations are increasing. I just want to be clear that carbon dioxide is a well-mixed gas. So when you increase CO2 in any individual location, it eventually spreads over the entire planet. But if you have a sustained source from one region, you also can detect kind of a local maxima in the amount of CO2. And so, yeah, these data are the data that I produced and averaged and produced for you guys, curated for you guys to kind of think about this question of the spatial pattern that John was so nicely motivating at the beginning. Some take-home messages. The spatial pattern of surface warming does not match the spatial pattern of surface greenhouse gas increases. And so we could talk about that. It sounds like you guys already have about why, some of the reasons for that. In recent decades, greenhouse gas increases by humans are largest, unsurprisingly, over the regions where there's kind of the most industrial activity and there's the most people. And then also, that's interesting because that's not where the globe has warmed the most. In fact, the regions of the globe that have warmed the most are the high latitudes, the Arctic, and overall land areas. The land tends to warm faster than the ocean because the land is easier to warm than the ocean because it has a lower heat capacity. So I'll stop there. I'm happy to take any questions. I hope that this was interesting and useful for you. And yeah, thanks so much, John, for the opportunity, and you all for your time.
Yeah, thanks, Dr. K, so much. It's so comforting to have you come speak after I speak because you clarify so many things. I hope that folks took as much from that talk as I did. Does anybody have questions for Dr. K about her work in this context, about the data visualizations she showed at the end that are also in the data puzzle lesson? Anything while she's here? Well, Dr. K, I have a question for you.
Okay,
And,
John.
and this is when you are curating these data sets for the Arctic, are you using temperature, CO2, in the case of shortwave and longwave radiation data sets that you're capturing? Are you averaging those for the Arctic between 70 and 90-degree latitudes, or are those specific to, in the case of the albedo data set that you curated, specific to the Arctic Ocean, or everything from 70 to 90 degrees?
Yeah, that's a great question. It kind of depends. Sometimes I just do 70 to 90 north. If you look at where 70 degrees is, 70 degrees north, it basically traces the coast of Alaska and Canada. So it's a good proxy in that region for like the land sea. But of course,
Huh.
70 degrees north includes a lot of Greenland. So yeah, that's definitely important um, here. And so you can remove the influence of the land by area weighting the grid cells and just including the region and the component of that region that's related to the ocean. I also want to say for all of this, I'm area weighting because the amount of area from 60 to 70 degrees north is a lot more than the area from 80 to 90 degrees north because of the convergence near the poles. And so that's kind of a good thing to keep in mind if you're ever trying to do these kinds of calculations, that you need to cosine weight the latitude in order to area weight things appropriately.
Great. Thanks so much, Jen. And I added a link to the lesson that the data sets that you were referring to earlier are included in, albedo, sea ice extent. So there's much more. Jen has curated a really comprehensive data sets for the Arctic that we've integrated into different lessons. Jen, in the chat, I just wanted to call out Erica. Said that the favorite part was seeing the Arctic ice over the US. It was really cool and helpful context, and a number of people hearted that in the chat. So that was really cool to see, and really fun to imagine. I can't really imagine being in the Arctic in total darkness, conducting work in that space, and crazy for me that it's October 8th and that's happening already. Carla asks, what's the stability of these data sets? And we can
That is a
ask
great
for.
question. I think for a lot of my career, I've just kind of taken them for granted. Again, I mean, I was born in the late 1970s, and so, I finished my PhD in 2006. That's when Series, had just come online. There were only 5 years of data at that point in time, or 6 years of data. So, it was still a really new and exciting data set. And now, like, just what we can learn by having these data over a longer time period, it just really helps us understand what's going on, what's changed, what's variability, how these different things come together. And, I don't really want to get into politics here at all, but just to say that I think observations are really critical to understanding what's going on. And observations are definitely something that I'm more concerned about the longevity of the federal government supporting right now. So just encourage you to think about that and just know that, like, we should all have observations, how we react to them and what we do with them, if we're not based on the same kind of common ground, that's going to be really challenging and make understanding what's happening much more challenging.
Great. Thanks so much, Dr. K, for being here. It is the top of the hour. I want to respect everyone's time. And again, just express appreciation and gratitude for you all for being here this evening after, again, a long day of work. Many of you coming from classrooms. It's a lot to come to one of these events after work. So really appreciate you being here. In the chat, I've included a link to a Google form for those of you that would like a certificate for 1 hour PD certificate for being here tonight. Please add your name to that Google form and I'll send that out either tonight or tomorrow. And wanted to plug, I'll have another data sense making webinar focused on a data puzzle lesson called Mega Drought in the Colorado River Basin, and the scientist who curated that data set, Seth Ahrens, will be a part of that. So we're running a series of these where we focus on some different strategies and lessons, and then bring in the folks that helped curate the data set that have that wealth of scientific knowledge to provide some additional context. Jen, thanks so much for being here. So
Thanks so
good to
much,
see
John.
you.
Have a wonderful evening,
Really appreciate
everyone.
you. Yeah, thanks, Jen. Bye, all.